All right, let's dive right into this. Have you ever looked at a massive Python codebase and wondered how in the world senior engineers keep it from completely collapsing under its own weight as it scales? Well, welcome to this explainer. Today, we're shifting into premium tech tutorial mode to completely demystify one of the most powerful, yet honestly kind of misunderstood concepts in object-oriented programming, and that is polymorphism. We're going to break down exactly how to use it in real-world production codebases so you can write cleaner, faster, and just infinitely more flexible applications. So if you're ready to seriously level up your Python skills, make sure to hit that subscribe button and let's get started. First things first, think about the complex conditional logic you might be writing right now. What you're seeing here might look functional on the surface, but it actually contains a massive hidden vulnerability that will absolutely break your application as it scales up. Every single time you add a new payment processor, a new database connector, or a new notification medium, you have to dig back into your core codebase and modify endless if-elif blocks. It's a nightmare. It breaks your app, it introduces sneaky bugs, and it slows development to an absolute crawl. And here's the thing, this structural weakness, it's almost always caused by a failure to understand polymorphism. And this brilliantly illustrates the exact solution. On the left side here, you see a really bloated, tangled chain of conditional checks. We call this the look before you leap style. You're asking exactly what an object is before doing anything with it. Honestly, it's brittle and it's slow. Now look at the completely streamlined approach on the right. This is Python's easier to ask for forgiveness than permission style. It's just a clean, two-line polymorphic method call. We literally just ask the object to calculate its shipping, and the object handles all the details itself. It is beautiful, it's simple, and it's incredibly scalable. To really wrap our heads around this, think of polymorphism kind of like a standard electrical wall outlet in your house. That wall socket provides a consistent, predictable physical interface, right? It absolutely does not need to know whether it's powering your laptop, a reading lamp, or a kettle. Each of those devices implements its own internal logic for how it actually consumes that power. The outlet simply exposes the standard contact points, and the devices adapt to it. Well, in software engineering, polymorphism works exactly the same way. It provides a standard software interface for objects to process requests in their own specialized ways. So let's actually anchor this with a solid definition before we move on. Polymorphism comes from the Greek roots poly, which means many, and morph, which means form. So it literally translates to many forms. In programming, it's simply the ability of different objects to respond to the exact same message or method call in different, highly specialized ways. Basically, you call the exact same method, but the resulting behavior changes completely depending on the specific object receiving it. Now, you might not realize it, but Python actually has this concept baked right into its core. Take a look at function polymorphism here. The built-in len function is a perfect example of this. If you pass it a string, it counts the characters. If you pass it a list, it counts the elements. You don't have to call a specialized lenString function or a lenList function. The single len function dynamically adapts to the input data type and just behaves appropriately. It's doing the heavy lifting for you. Which brings us to Python's totally unique flavor of dynamic polymorphism, famously known in the community as duck typing. You've probably heard the old saying, if it walks like a duck and quacks like a duck, well, it's a duck. In Python, the interpreter really doesn't care about what an object strictly is or what class it inherits from. It only cares about what an object can do. If the object has a calculate shipping method, Python is just going to let you call it. No questions asked. Now, what's really interesting about this slide is the crucial difference between strict inheritance and duck typing. On the left, we've got inheritance-based polymorphism. Basically, every product has to inherit from a base product class just to guarantee it has the right method. But on the right, utilizing duck typing, we have completely independent book and t-shirt classes. They don't share a parent class at all, but they both just happen to share a calculate shipping method. This saves so much development time, drastically reduces type coupling, and lets you mix types from completely unrelated libraries effortlessly. Of course, if you do actually use inheritance, you're going to rely on method overriding. Here we have an animal parent class with a generic speak method, but the dog class, which inherits from animal, defines its own speak method to bark instead. When you call speak on a dog object, the child class actually intercepts that method lookup. It overrides the parent to provide its own specialized implementation. This is super powerful because it lets you treat a whole list of different animals uniformly, while each one goes ahead and executes its own specific behavior. Let's move to and see how this builds into Python's syntax itself with operator overloading. This is a game changer. When you write A plus B, Python doesn't just do hard-coded math. No way. It translates that plus sign into a method call, completely behind the scenes. Notice how the plus symbol maps directly to the double underscore or dunder method underscore add. The minus sign maps to underscore sub, and the asterisk maps to underscore mul. By defining these dunder methods inside your own custom classes, you get to dictate exactly how standard mathematical operators interact with your objects. Let's actually walk step by step through how Python resolves these operator calls behind the scenes. Step 1, the interpreter encounters the expression a plus b. Simple enough. Step 2, it actively checks if the left object, a, has an underscore add underscore method that knows how to handle the object b. Step 3, if a doesn't know what to do, it doesn't just instantly crash your program. Instead, it returns a special singleton value called not implemented. Python then smartly falls back to check if b has a reflected method called underscore radd to handle the operation in reverse. I mean, it is just an incredibly robust system. Okay, but here is a massive gotcha. For those of you transitioning from statically typed languages like Java or C++, Python has a major overloading secret. It actually does not support native method overloading based on different parameter signatures. Why? Well, because inside a Python class, methods are quite literally just stored in a dictionary using the method's name as the key. If you define a second method with the exact same name, it just overwrites the first one in the dictionary. It's like replacing a puzzle piece with a new one of the exact same shape. The last definition wins. So how do we handle situations where we really need different method signatures? Well, we simulate it. Modern Python developers use a few really clean alternatives. You can use default arguments or pack variable inputs into args and double quirks. But if you want a truly elegant solution based on the input type itself, you can import the @single-dispatch method decorator from the functools library. This is awesome because it allows you to register totally different behaviors based on the type of the first argument, giving you powerful overloading without those brittle if-else checks we talked about earlier. Now let's zoom out and look at enterprise-level application scaling. On the left side here, we have an absolute nightmare. Tangled, hard-coded payment integrations for Stripe, PayPal, and a dozen others, just scattered all throughout the checkout logic. On the right, we apply polymorphism using something called the strategy pattern. We decouple the core business logic from the concrete implementations. Your checkout engine just calls a unified .charge method, and the specific payment gateway object gracefully handles all the complex API details. And here is the best part. By designing your systems this way, you are perfectly adhering to the open-close principle, which is literally one of the foundational rules of solid architecture. Your software becomes open for extension, meaning you can easily just pop in a brand new cryptocurrency payment gateway, but it remains closed for modification. That means you never have to touch or risk breaking your existing checkout flow to add it. Polymorphism is the key that unlocks this entire pattern. But I can hear some of you asking right now, what about type safety? Historically, duck typing's incredible flexibility had a bit of a downside. Static type checkers just couldn't verify it, but that completely changed with PEP 544, which introduced protocols. Protocols essentially formalized duck typing into something called structural subtyping. You can define a protocol class that specifies exactly what methods an object should have. And now, your static tools like MyPy can verify polymorphic relationships without requiring you to build out those rigid inheritance hierarchies. It really is the best of both worlds. Listen, if you're building real-world Python apps, or maybe you're interviewing at a top tech company soon, you absolutely need to know how to talk about this stuff. So let's cover some advanced interview secrets. First big question. How does Python's approach to polymorphism actually differ from languages like Java or C++? Okay, here is the exact senior engineer answer you want to give. In Java or C++, polymorphism is usually resolved at compile time through static nominal subtyping. Basically, that means it relies on explicit interface declarations and rigid class inheritance trees. Python, on the other hand, resolves method calls dynamically at runtime using duck typing. It manages namespaces via dictionaries, allowing literally any object that implements the required method signature to participate, totally regardless of its class ancestry. Drop that in an interview and you are golden. All right, here's another really challenging one that trips up a lot of developers. Interview secret 2. When you are dealing with multiple inheritance and overriding methods, how exactly does the super function resolve which method it's supposed to call? So the crucial point here is that super does not just blindly call the direct parent class. Actually, it dynamically queries the method resolution order, or MRO, of the active instance. Python constructs this MRO using an algorithm called C3 linearization. It's a mouthful, but basically it guarantees a strict deterministic search sequence. Super finds the current class in that chain and simply passes control to the very next class in line, creating this really elegant cooperative inheritance chain. Wow, okay, we've covered a massive amount of ground today. Let's do a rapid-fire summary of the top takeaways. You might actually want to take a screenshot of this cheat sheet. 1. Python prefers dynamic runtime polymorphism over static compile time checks. 2. Duck typing means focusing on what an object can do, not what it is. 3. Use dunder methods to overload operators like addition and subtraction. 4. Method overriding lets child classes customize their parents' behavior. And 5. Use the strategy pattern to completely eliminate nested if-else chains to keep your codebase scalable. I'll leave you with this final, kind of provocative thought. Go look at your current project. Where is that massive, brittle if-since chain hiding, and how will you refactor it into a clean, polymorphic interface today? Seriously, challenge yourself to apply this knowledge right now. If this explainer helped you master Python's polymorphic behavior, make sure to smash that like button, subscribe to the channel, and share this with your engineering team. Keep building great things, and I will see you in the next one.